So of course I'm looking at this book. This is day 3 or 4 of, I guess it's day 4. I've been making good progress, I guess because it's still pretty easy. Um, we did 15 last time, and I somehow missed, I've done some of these before, like the first about 30 problems I did in the past, like 2 years ago or something. And I remember missing that word last time too. But maybe not, I don't know. I'm pretty sure I remember. So like, it was like you do a set of weights, and you want to show that there's a unique way to represent a number as the sum of these weights. But that's not quite what he says. He says using both pans. So we had this scale analogy, where you can put weights on both sides, like a left pan and a right pan. Anyway, that corresponded to a different series, a different generating function, the dn's. So if you're only allowed to add, which is a bit like partitions of a number, you use this cn series and you get a product. They're both very similar, but if you're allowed to like subtract from the number, then you include values like -1 in your variables when you're looking at an equation like this. And in your expansion, they look like this. So that was the answer to 15. I'm not going to go back over that. I forgot to look at why this explicitly is the number, but it's probably not a super interesting computation. You got to stop somewhere for a particular lower value, for like a particular n. You only need a finite number of terms. So we're on 16. Gonna see how this goes for me. Looks like 18 involves that, like I was using a similar formula for each of these chunks back in 15 and 14. So 18 is not going to be bad, but I don't know about these. Looks like there's 2 applications somehow. But alright. That's an interesting one. Alright, well, these might be quick if I can interpret them correctly. I don't think I had anything to follow up with you on last time. I didn't have any questions at the time, so we're just going to move on to 16. Says to yeah, well, anyway, 16 asks you to write this, how well you can read that. Yeah, maybe it's in the distance, I don't know. It says write 1 plus q zeta times 1 plus q zeta square times 1 plus q zeta to the 4. So those are powers of 2. Yada yada. So if you expand this, say you get a series, a0, a1, zeta, a2, zeta square, and so on. What is an? Find an. So I recognize this now. Without the q's, that would be... Without the q's, the an's would represent... well, actually, I guess they would all be 1, wouldn't they? But they would represent the number of ways to solve an equation, like number 14 back here, when it was asking how many ways can you solve this equation, but the weights are powers of 2, so like 1, 2, 4, 8, 16. And if you set that equal to a specific number, an integer, or really I should say a natural number, there's only one unique way to express that as powers of 2. With the q's there, so if you did expand this out, you'd get, let's see, 1 plus q, you'd get like, just as a comment say, you'd get 1 plus q zeta, that's times 1, and then times this part, this chunk, you get a single q zeta square, you get 2 q's here, zeta to the 3. That's this first 2 terms. And then if I multiply here, you get themselves plus q zeta to the 4 times the whole thing. So you get a single q zeta to the 4, 2 q's here on zeta to the 5, and zeta to the 6. And then suddenly you get a third q for zeta 7. That's the first 3 factors. If we do it again, I'll stop there, but we're going to get another 8 terms this time. We get these times 1, and then you get these times q zeta to the 8. So a single q zeta 8, double q zeta 9, double q zeta 10. I guess triple q on zeta 11, and then we have a single again, so it's q squared zeta 12, q cubed zeta 13, q cubed zeta 14, and finally the biggest one yet, q to the 4 zeta 15, and you'd keep going. I'm just going to stop expanding at the moment. So what are the ANs? Obviously they're some power of q. So you get, so let's see, AN is q to some amount. Let's call it like f n, some integer number, where fn is it's like the number of interactions that we had up here. Oh, yeah, right. Okay. The Q is keeping track of whether you used this number. When you take a couple pair of these, like when you take a selection of these numbers, you get some result, right? Say you get this power that comes from, like say 13 is the exponent. That's the result of adding some numbers together. So this is kind of analogous to having that equation like E1 plus E2 times 2 plus 4E3 plus 8E4, etc. And you're only allowed to put zeros or ones there. So you're getting like a binary representation of the number. So for instance, for 13, the unique way to express that is probably 8 and 4 and 1. So you get like 1, 0, 1, 1. Here, I don't know, I'll put a B here. We'll say it's equivalent to 1, 0, 1, 1 in binary. And the sum of those, like we have a single Q each time that factor was used. Each time this term was used in the sum, this factor is used in the product that you get. So for instance, for this one, the sum is 3. So Fn is the number of times there's a 1 in your binary representation. Uh, 17 says, consider the expression 1 minus a times 1 minus b times 1 minus c. Okay, so it's going to keep alternating, sort of. That second term I'm saying is going to keep alternating. When you multiply it out, it's going to change the signs of things. The first one just kind of preserves the old stuff, just like we did here. Okay, so look at 1 minus a, 1 minus b, 1 minus c. He stops there, but we could keep going. And when you expand this, of course, you get 1 minus a minus b plus c, plus ab. So that's the first two, and then times itself, and then times minus c, you'd get minus c, and that's what I was saying, like these alternate, like plus ac plus bc minus abc, right, negative c times this part is minus abc, it goes on, obviously. Anyway, our question is, what is the sign of the nth term? Sorry, on this one, I'm seeing something like this gets repeated. That was the first factor. Plus then minus. And then it gets sort of doubled. So this was 2. When you go to 4, you get the reverse image of this. So I know going to 8, we're going to get just the opposite of this, minus, plus, plus, minus for the next, for terms 5 through 7. 5, 6, 7, 8, sorry, 8. 5, 6, 7, 8. And then it repeats, like, so for 16, you're going to get these same symbols, but the opposite signs. So like this repeats, but it's just opposite signs, like minus, plus, plus, minus, plus, minus, minus. So I want to pick a particular one, like the nth one, and describe what the sign is going to be. Alright, say I take like the 7th, we're here. It corresponds to the previous sets. 7 is 3. Like the 7th entry corresponds to the 3rd entry. It's the opposite of it. And then if you're on if you're on the 8th one, I guess it corresponds to, alright, if you get 0, you're right on 4. Oh, that makes sense, so mod, it's the sign opposite your number, mod, whatever the largest power of n is, don't call it n, but largest power of n, oops, 2, excuse me, largest power of 2 less than your number, less than n. What is the sign of the nth term? There's probably a closed way to express that. So like if I was on 4, we mod 2, we get 0, and it basically tells me that it's the opposite of whatever you get here. So like, let's call it S. S1 is of course positive, S2 is negative, and the rest of them are defined in terms of these. I wonder if I could do the same thing like as the previous question and somehow like because 7 has an odd number of 1s in its binary representation, we're going to get, no, it's not going to work, but I assume, well, let's try it again. What else has an odd number of terms? Is 13 8 plus 4 plus 1? So what would 13 be in my technique? Like 13 mod 8 is 5. So I would be looking at the 5th entry, and I'll do the opposite of that. It gives us a positive sign for 13. Like the 13th term, which I did write it out. It's this is 8, 9, 10, 11, 12, 13. So there's the 13th one. So, alright, fine. Okay, I feel strange about this. I don't really believe that this is working. Well, it might work actually. So we start with these, and then every other number, what I started to do is I modded it by the largest power, and then I just referred to the previous set, and I took the opposite sign. I just can't help but think it feels similar to what we just did here. What if I just let, like QB1, no, don't do that, you lose information. But still, something like this where I let, these are just powers of zeta. Yeah. You're doing the same thing. Wait a minute. Yeah. So like the number of times that this hits is the number of negatives that you have. So if you thought about this in terms of this powers of 2 thing, yeah, I was right about this. I was only thinking about it because I just did 16. But how do I say that cleanly? Like, yeah, just let A be this and B be this. Like let A be negative q zeta, and let B be negative q zeta square, etc. And you'll be looking at question 16. And then the coefficient will be like the negative that determines the sign. That's what we're after. We're trying to find out what the sign of the nth term is. But you'll have a negative the same number of times that you have interactions, or like basically it would be this question again. You'll have a negative the number of times that a 1 shows up in your binary representation, which is consistent with what I just did, but let's... No, that can't be true. It's wrong. It's wrong. It's wrong. Because like 4 is wrong, right? 4 has 1 negative and it gives me a positive, which I guess is what I just said. Damn it. Okay, but 8 doesn't, right? 8 gives me a negative, even though it only has 1, 1. So I'm wrong about that. Okay, so it's not that simple. But it's kind of close. Huh. Oh, I could still account for that. I could just say which set of, like which set are you in? This is 2 to the 0. Well, you know, this is 2 to the 1. 2 squared gets you to 4. 2 cubed gets you to 3. So like you belong to a particular set, particular range of, and it ends at some power of 2. And so like the first one, if you're, this is 2 to the 1, that length, and it ends on a negative. So which means 2 squared is going to end on a positive. 2 cubed is going to end on a negative. That'll be the 8th number, you know. Yeah, I don't know. This didn't quite work. It was an interesting idea. But now what I'm saying is, I don't know how I would express that in some clean form, though. So like another example is 4 is 2 squared, and because that's even, the sign is going to be, let's see, this one's odd, and we get a negative. So this one's going to be, the fourth one is going to be a positive, right there. Another example would be like 3, you mod 2 and you get 1, and then we look this up here and we take the opposite sign. So because s of 1 was plus, 3 is a negative, which is probably true, yep. So I'm right about this rule, but it's kind of a mouthful. I'm saying like, take the sign opposite to number, mod, whatever the largest power of 2 is. But that means you need to like refer back to the previous set, the previous range from 1 to this largest power of 2. So it's a recursive procedure here. All right, it's been a few minutes. I guess I'm tempted to just look to see what he said. So for 15, oh, we did that last time. For 16, the coefficients, this was the Q problem. 1 plus, you know, it was a series with like binary powers, like 2 to the 1, 2 to the 2, 2 to the 3, etc. And in a sense, we're just counting the number of times a Q shows up. So he meant to write Q here, for sure. He did the same thing with this trick. All right, anyway. Let's see if you guys can see this. Boop. All right, so I'm looking at 16. Well, it's supposed to be Q. Q to the Fn, where Fn is the number of digits 1 in the binary representation. Yeah, that's what I had said. Not bad. That was a neat problem. 17. Catalan solved by Cesaro. That's interesting. Series of question results from this expansion, and then just allowing it to be 1. That's really similar to the one that I had just looked at. Anyway, determine the sign. Fisher examine the case where all the numbers are 1. What? According to 16, sure, the sign is given by a negative sign to the power, where this is the number of 1s in the binary. Huh. kind of what I had said, but I didn't believe it was true. I mean, I know that it's not true, actually. Because if you take something like 4 or 8, they behave differently, even though they both have a single 1. As for these being 1, that's true. The specific, that's true, they could be 1. That doesn't actually affect anything. If they are 1, you basically get the same series as 16, except there's a minus sign instead of a plus sign. So yeah, there's something fishy about this answer. Oh, no, I'm still right. Yeah, this is not true. That's not true. If you look at, I just showed that was wrong because here's 2, here's 4, here's 8, and they behave differently. Here's 16. They alternate. I wonder why that answer is wrong. That's so weird. It's really close to right. It depends on which set you're in. What I mean is, actually, that's a better way to think about it. Like that actually is much faster than me saying, oh, just refer, like it's a recursive thing, and you just refer to the previous range. That doesn't really work as a formula. But here's what I mean. Here's how I know he's wrong about this. So it's true for 2. For 2, you have just, in binary, it's, here, I should just write it like this. And 2 is what, the number in binary. And there's only a single 1. And so you'd expect it to be negative, and it is, correct. But when you look at 4, that number is equivalent in binary to 1, 0, 0. And there's a single 1, but the sign is not negative, right? The sign is positive on 4. He was saying it's negative 1 to the number of times that your number has a 1 as a binary representation, and 4 is wrong. 2 would give you this, 8 will give you this, but 4 will give you the opposite of this. So it depends on where it depends on the power that you're actually talking about. For even powers, and even for 1, right? Even 1 is a counterexample. 1 in binary is just 1. But you don't get negative 1 to the 1 as an answer. You actually get the opposite of that. You get a plus sign. And the reason is this power of 2 is the 0th power. It's an even power. So how do I... Well, okay. So all it means is you look at the range that you're in. This is definitely a better answer than what I was saying, because I was like, oh, mod, and then look at the previous range. But this is very close to the correct answer. But you have to sort of adjust by which range you're in. And to determine that, you just say all right, the smallest power of 2 that's, the biggest power of 2 that's less than n. If it's an even power, then you do the opposite of this. So let's call it a sub n again. A sub n is just the sign of the number. It's a negative -1 or +1. But you get this in a certain case, and you get this in the other case. You get this if, and sorry, I didn't write it down. Fn is again the number of ones in your binary rep. So you express n as a binary number and you count the number of ones. So I agree with him. I need a short word for this. If the largest power of n less than your number has, let's say, odd n. So let's test this again. So if you're on the third term, the largest power of 2 that's less than 3 is 2. It's 2 to the 1. Because that's odd, lost my train of thought. When it was an even power, it was wrong. Well, one of these is if it's basically even and odd, and I can't remember which. So one of these I'm going to write if it has an even power, and one of them I'm going to write if it has an odd power, and they swap. And that's about it for this problem. But I don't know why he... I'm just wondering why they wrote this when it's clearly not correct. It's not just the number of ones, it also depends on like where they're situated in a sense. I mean, I guess you could just multiply by another power of 1, right? You could say like times -1 to... Actually, you could literally just do the same power. -1 to whatever. And if it's even, it'll cancel. And if it's odd, it won't. So was I going to think this through and figure it out? I don't know, man. My brain is kind of melting from this problem at this point. So let's try it one more time. So if you have 3, well, okay, in the new method, what you do is you realize that 3 is this number in binary that has 2, so we get -1 to the 2. -1 squared is +1, so you'd expect it to be positive, which it is not, by the way. According to the formula in the answer, 3 would have a positive term, which it doesn't. And I'm saying it doesn't because the largest power less than 3 is 2 to the 1. If, let's see, he was telling us 2 should be positive, and I'm saying 2 should be negative. We're in this track. Sorry, 3 should be negative. And that's happening because the largest power of 2 has an odd n. So let's try one more. If you looked at the number 8, which of course is just 0, well, it's just a 1 with a bunch of zeros after it in binary. So this is just 1, so your number would be 1, so you'd expect 8 to be negative. However, 8 is also 2 cubed, and because that's odd, it's going to flip the sign, and 8 will be positive. Damn it, I screwed it up. Okay, so it does actually have to be less than. The largest power of 2, strictly less than your number. When I did 8, we would use 4. That's 2 squared. Since that's even, we just get what the formula predicts. In the case of 8, that's a negative sign on the 8th term. That would be correct. If we went with like 7, I'm sure I probably wrote here, it is, yeah, 7. If you use 7, you get, I don't know why you're modding. Sorry. 7 in binary is like what, 4 and 3? So you get 1, 1, 1, 1, like that in binary. So because it's 3 numbers, this is an odd number, you're going to get a negative. So the formula would predict that the seventh sign is negative, but that's going to be wrong. And the reason you need to use my formula instead is 7 is bigger than 2 squared. 2 squared is the smallest power, or sorry, biggest power that's less than 7. Because that's even. Damn it. What just happened? What is happening? Did I get it wrong again? Huh. How did I screw this up? 2 to the 1, 2 to the 2. I was pretty sure I had this correct. How did I... Well, now neither of us are right. Interesting. What? I don't know, man. Another one is like 6. 6 is, in binary, it's 4 and 2. Right? It only has 2. So his formula would tell you that these behave differently. But they don't. 6 and 7 have the same sign. Also, this is proving that my formula doesn't work, right? Shit. Alright, I'm going to move on from this. But this 17 is a little tricksy. It's weird. It's very strange. No, he's right. His explanation makes perfect sense. You just let q be -1. I don't know why he didn't specifically mention that, but I guess you don't need to. It's 1 plus zeta. It's 1 plus q zeta, 1 plus q zeta squared, etc. Where q is -1, and then you just count the number of times that q occurred. So this has to be correct. So why is it not working? Like 6, I mean, yeah, his explanation actually makes perfect sense. So if he's right, why does the formula not work? So for instance, for 1, it doesn't even work for 1, right? 1 would give you, 1 is just 1, so 1 should be negative, but it's not. So maybe he's counting from 0. Like this is the 0th term, and 1 is negative, but then 2 is also negative. Okay, 0, 1, 2. Okay, then 3 is not. 3 is positive. Okay, yeah, I'm just being an idiot. He started at 0. That's good. Indexing from 0. In a math book. Can you believe it? Okay, good. That explains my shift in 6, 7. Like, this is the 6th term now, and the 7th term is different in its negative sign. And the 8th term is also a negative sign. That's correct. And then like 9 would have 2, so it's even. Okay, okay. Yep, it's this. It is this. You just have to index correctly. Good. Glad to see I figured that out after like 10 minutes. Alright, lads and lasses, let us continue the adventure. Oh, thank God. Alright, 18. Prove the identity. Finally we have some algebra. Finally we have just something simple. So first of all, another way to write this with the 10 terms is going to be like this. And I'll put probably zeta to the 10 there. That way when you multiply this by the infinite series, when you multiply the top part by the infinite series, you get itself minus zeta to the 10 times itself. So everything from 10 on gets deleted, and you're left with just zeta 9 and everything previous. So that's correct for the first factor. Then he multiplies it by, and this time we have powers of 10. So downstairs in my little geometric series, according to that. But again, upstairs, we're going to chop off everything above 100. So if I put 100 here, that should do it. And now when you look at the expansion, the geometric series with powers of zeta to the 10, oh, you can't see what I'm writing. So you expand, forget about the top for a moment. Suppose it was just 1 over that. You get this infinite series of, it looks like that, but it keeps going. And then if I subtract zeta to the 100 times itself, you get a zeta to the 100 term that you're subtracting, you get 110, 120, etc. So all of those are removed. So this is correct. And then I'll stop on this third one, but he continues. 1 minus zeta to the 100, we're going to remove probably 1,000, right? 1 minus zeta to the 1,000 equals what? So after these all cancel, you can see that you're getting 1 over 1 minus. There's really not much to this proof. That's pretty much it. Should I even look? 18, that's exactly what he wrote. This problem is not contained in 9. The result is well known. Any positive integer admits a unique representation in decimal. Sure. Sure. So like here's your first digit, here's your tens digit. Interesting. And then on the right is just the integer itself, the natural number itself. Any positive integer admits a unique representation in decimal notation. Also see 14. Yeah, 14 was the weights with like the same question but in binary. Okay. All right. 18.1. First and third problem are considered in the solution of 9. Sure. Are the extreme cases of a common generalization which, when extended, includes this. Formulate such a generalization. First and third in problem 9. That was the one where he just generalizes everything we had talked about, so the 4 problems. First and third, the ones that he calls AN and CN. So AN was making change. It was like find the number of non-negative integer solutions to this kind of question. And so we generalized it. There are extreme cases of a more common generalization. I don't really get what we're driving at here. Well, I mean, I kind of see, obviously, like this is the same formula we used in question 1, the AN example. And CN was the one with weights, but you're only allowed to add, which is actually similar. It's kind of the same thing. What is he trying to say here? There are L kinds of coins, and we've limited a number of each kind, P1 of each kind. P1 of the first, worth A1, etc. How many ways can we pay n cents? So given these integers, find the number of solutions to this equation. Okay. To include, so he's just saying those were finite examples, I guess. And then for this particular example, A1 is 1, A2 is 10. Yeah, maybe this is so obvious that I don't know why he's saying this. But that's a cute formula. So yeah, particular cases, yeah, you get CN when you let all the, I guess you can call them, well, yeah, I'm a little confused by that. Oh, okay, yeah. This one, we had sort of you sort of need to consider all the terms. You only need a finite number of them for a fixed n, but we had let the series be infinite. So I guess in some sense you never truncate this. You just get 1 over or whatever. If you look at your answer back for number 4, sorry, not 4, for number 1 basically. These are infinite series, so you get a product like this. Oh, you can get dn back as well. If these are all he's saying 2, so that this becomes a 3, so that we get like 3 terms. And then if you allow the, right, 18 has to do, I mean, you never actually terminate. You don't actually have a finite number of terms. You have like a ones place, a tens place, a thousands place, etc. So if you allow this to go off to infinity, 9 is the largest term. We have like 10 total terms starting from 1 in this in these individual factors. Alright, that's interesting. Yeah, in this particular case we're doing powers of 10, but we can do powers of 2 or 3 or whatever you want. Huh. Okay, so 18 is kind of reiterating number 9 in its generalization of all the things we've looked at so far. In an assembly there are 2n plus 1 seats and 3 parties. How many different ways can the seats be distributed so that no party attains a majority against a coalition of the other 2? Interesting. think I'm just going to read the answer on this one. You have an odd number of seats and 3 parties. In how many ways could you distribute them so that if it's 2 against 1, 1 will lose? It's a somewhat clear question. How many partitions of this odd number first of all have 3 terms? But I don't see what that has to do with 18. I guess I should see, huh? I'm not even sure I have an equation that would yeah, he says it right here, pretty quick. Yeah, I'm gonna have to think about that one again. That's a really interesting question, 18.2. I'll look at that one again. But we're going to move on. Let's do 19. I don't see it off the top of my head. Yeah, let's do 19. It says... it says 1 plus zeta times 1 plus zeta squared. So we're going through every power, which is kind of unfortunate because it gives you like combinations. But maybe the fastest way to do this is to try and interpret it in terms of his counting techniques that we just saw. The right hand side is just the odd numbers, odd powers expanded in, geometric series. So products of infinite series of odd powers of zeta. So the right hand side gives you a series like this. And then times the odds. It's always odd powers, so 3, 6, 9, and then 5, and powers of 5. Well, multiples of 5, and the 7s, etc. But they're not like primes or anything like that. Yada yada. So the right hand side reminds me of the question if we were allowed, sorry, this just continues, I didn't mean to cap that off. If we had like some multiple, basically just odd numbers, right? So here it's like we're solving x1 plus 3x2 plus 5x3, okay? And you want to set this equal to n. The coefficient on the right hand side of zeta to the n would equal the number of integer solutions to this. I should say non-negative natural, non-negative integer solutions. The right-hand side coefficients of this series. The left-hand side was, there's this overlap. So what's the other way to think about this? The left-hand side, if I were to expand that, I'm not going to write them out because that doesn't really help, but the equation that I would have been solving is more like you have this or you don't. You have 1 or you don't. You have the term 2 or you don't. You have the term 3 or you don't. So this is, again, a sum, but it's more like E1 plus 2E2, 3E3, and this time yeah, we don't stop for some reason. Okay. We allow the e's to be 0 or 1, and the coefficient in front of n will be the number of solutions to that equation. And somehow these are the same. That's wild. Yeah, that's kind of a really interesting question. So this one came about from the making change example, and this one came about from arrangements. Like this one's more like a permutation. This one's not. So this is sort of counting the number of ways. If you use the terms 1, 2, 3, if you use natural number terms, it's counting the number of ways that you can partition this number. This one, if the number is even, and these are even, or you include this 1. Why would these be the same, though? Wow, that's tricky. This is clearly the way to think about it. Like, the algebra on this looks like a nightmare. Or does it? No, it kind of does. If we multiply on both sides by this denominator, you get some differences of squares for all the odds, right? And you don't get that for the evens. Does that help me at all? Like I'm saying, it's also apparently true that the product of what it means is that this is going to happen. You leave the even powers alone, so this stay a plus, but all the odd powers become yeah, that's a square, I suppose, isn't it? Anyway, even powers stay the same, odd powers get doubled. that. Anyway, this infinite product is apparently 1, but that's definitely not more obvious to me. I don't know, should it be? That's interesting. This matches up with that. This matches up. Like, this 10 is going to match up. Each one of these is going to match up with uneven at some point. But it skips 1, right? Like, 4 gets skipped. I don't know. Does that even help me, though? Oh, it doesn't get skipped. It's right here. Yeah, there's 1 minus zeta to the 4, which if you expand it here, you get 1 minus zeta to the 8. This guy matches up there to give you the 12 that I said was missing. Huh. So yeah, this will eventually hit a plus 10. What? Wow. Maybe it is 1. Yeah. That's crazy that this is happening. This times that gives me 12. This times that gives me 4. Which gives me 8, which is my next term. So the 1 minus 8 that you get from these 3 factors matches up with the next term in the series to give you a product of 1 minus 16. 1 minus zeta to the 16th, which is the one that was missing here. It's crazy that this algebra is working out. What a fascinating question. But again, why is this true? I kind of want to say that this is the number of, well, it's not partitions of the number. I keep saying that, but it's not exactly true because you're not allowed to use more than one of the same term. So these sums only include, they include distinct terms. This left-hand side is the number of ways you can write a number as the sum of distinct terms. This one is the number of ways I mean, you gotta be a little careful because the order no longer matters on this one. But, well, did it matter over here? It sort of should have. Maybe I'm overthinking that. Yeah, no, the order doesn't matter here. I wonder why I thought it did. Because when we did this previously, it was with like this stamp question where the order of the arrangements mattered. I thought it was like number 3. How many ways can you arrange these things? Different arrangements of the same values are regarded as different. So like 2, 4, 2 is different than 2, 4, 4. Or, 4, 2, 2. So that's like the BN case. Notice he didn't include BN recently. So maybe I should forget about that. Yeah, I think I must have just had them confused. This is closer to the weights problem. Yeah, this is the weights problem. This is CN. For some reason I was conflating it with BN, problem number 4, but it's more like problem 6, or 5 and 7. Alright, so good. So the order doesn't matter. And what I was saying was still true. It's like the number of ways you can express a sum in distinct terms, but with one distinct term. You're not allowed to repeat anything. How is that connected to this? I don't really see. So we're looking at two approaches. I need to either see how these are the same question or make this expansion more rigorous. When you combine, it's all the odd powers that are combined, right? And they get doubled. So immediately they're only even terms, just by definition, basically. However, the ones that are 2 times some odd number, well, what about this guy? He's 2 times some odd number. So the ones that are 1 minus with 2 times an odd number, they came from the right-hand side, me multiplying by the denominator. I'm saying if you have 1 minus zeta to the 2, times an odd number, that came from the right-hand side. And on the left-hand side, you will have a matching 1 plus that eventually, because that just goes through every single power. So this takes care of all the odds. It captures all the odds. The ones that look like this. And it sort of converts them into this form. Actually, let me use the exact same, because that's where it came from. So I won't put an n here, I'll put a k. So you now have these things. This is an even, I guess. But it also is different from the evens that were there. So for each, wow, okay. So what's left is evens, and every one of them matches up. Like this will match up eventually. This 4 will, well, no, this 4 also has a mate because of these two. So he didn't come from, that's interesting. This one initially didn't have a pairing, but it does now when you take this product. So I guess what I need to show is I just really want to show for any any power on the left that started as 1 plus zeta to some power, like for every natural number can be expressed as a power of 2 or something. I mean, written in binary is what I meant. That's kind of close to it. It's a confusing way to word it. So yeah, the powers of 2 definitely get caught. If you're not a power of 2, well, this guy got caught because, yeah, I can see that it's happening, that you're getting 1. I mean, you're getting 1 minus zeta to some infinite even power, which also gets canceled if you keep going. In a way, you get something like that, but like all the odds are taken care of, and so for instance on the left, well, somewhere along the way we'll have a 1 plus zeta to the in general, it's like here's its prime factorization, how do I know that that's going to match up with something with a 1 minus? This is just a small example, but it looks like 20 is going to be just an application of 19. Each positive integer can be decomposed into a sum of distinct positive integers. Yeah, in as many ways as it can be decomposed into a sum of odd positive integers to a sum of equal or odd, or equal or different. So meaning you could have multiple. So like this counts 1, 1, 1, 3 because those are equal terms, but this is a distinct term. So every number can be decomposed into a sum of odd positive integers. That's this right-hand side, and distinct positive integers in general. That's this left-hand side. So 20 is immediately clear from 19. I'm just glancing at 21 here. 21 doesn't seem to be quite the same. You can write an integer in this many ways as a sum of smaller integers. Two sums that differ in the order of terms are considered different. So when he says write it as a sum, he means like an arrangement. So for instance, the number 4 should have 2 to the 3 minus 1. That should be 7 different ways to express it. yeah, this is tricky. I have a feeling 21 is going to relate to 22. Maybe. No, maybe not. Maybe not. Never mind. Yeah, I'm not sure where 21 is coming from. As a sum of smaller integers. Well, yeesh. Okay. I'm getting kind of lost here. I can see that they match up, but so like I can see all powers of 2 are filtered out. What I mean is they become 1 minus zeta to some large power of 2, which keeps matching up with another power of 2. So you get like a sieve type effect. And that captures, I shouldn't have put a dot here, but it captures these ones. And then there's an 8 here, that's another dot. These guys match up to give you 12. So that's like, that's a single 3, you know? 3 is a factor. I mean, if you want, we could keep going with that. This gives you minus 12. Yeah, minus zeta to the 12th. And because 12 is an even power, here's an 8, 10, 12. You know, 12 is like the third term that I didn't, the third factor that I didn't write here. But my point is, that then gives you 24. It's giving you the numbers that have 3 as a single. 3 to the 1 is a factor in this exponent. So it's 3 times powers of 2. This 10 matches up with another one. So let me put like a double here. But this is a multiple of 5. So this factor is about to capture all multiples of 5 and turn them into this form, 1 minus, you know, so it's behaving sort of like a prime sieve, if that makes any sense. Interesting. Alright, let me see what he has to say about 19. Does he have multiple solutions to 19? He's got 3 solutions explaining his answer for 19. I just skipped to the third one just to see how weird it was. This is of course true, but then I don't quite, what? I don't quite follow the last line, I guess. Oh, yeah, okay, sure. What? This is, okay, this is a much more clean explanation than I was saying. What else? So his first answer is from Euler, I guess. According to 14, like the weights, I guess this is the unique binary thing. Sure, I get that. If you do this with threes, you'll get this series instead. Yeah, that's true. Sure. It's actually, that's pretty clear. And so, wait, what? He's done? Oh, interesting. That's clever. Okay, these are multiples of 2s, 3s, 5s. Okay. Yeah, I should probably learn these tricks. This is pretty straightforward stuff. And then the second example looks like what I was doing. If you expand this, you'll get 1. Yeah, this is what I started to write out because I multiply by the denominator right away. Sure. I mean, I didn't do it this way at all. When you write that out, yeah, sure, you're looking at just 2 of these. Right. Oh, sure. I see. I was wondering where the 0 came from, but he's saying, for instance, if zeta was less than 1, this is a continuous thing, and so you're going to have to get k of 0. Wow, those are really interesting solutions. I'll have to go back over those. I don't know if I'm going to actually review them on screen, but we'll call that a day. That was 19. So we made it 16 through 19 today. And well, 20 is also, let's just look at 20. Is he going to say anything? Interpret the coefficients in the previous problem. Yeah. Result states exactly that. Yeah. Okay. So I'm going to include 20 in our adventure today. That was 16 through 20. Wow. Thank you all for tuning in. I'm going to call it a day. Have a good one.